All right, returning back for our third and final video with looking at continuity and doing proofs of continuity. So I again have my definition over here to the left. I've listed again my default kind of basic functions that I know are always continuous. So just kind of as a reminder for me. So here we have our f of x, and we want to ask the question, is it continuous at x equals 1? So I have 2x plus 3 when x is less than 1, and then x squared when x is greater than or equal to 1. So is this continuous at 1? So first, I see that these two pieces are in fact continuous functions. They're both polynomials. So I'm just kind of keeping that in the back of my head. So no asymptotes floating around anywhere. The question is, do these two pieces connect nicely at this x equals 1? So starting with the first condition, does f of 1 exist? So when x is 1, yeah, it does exist. I would be plugging it in here. So it would be 1 squared, which is 1. So the first part, first condition, you have a function value at that point. Now, the second condition, does the limit as x approaches 1 exist? And that's my question. All right. So we're going to have to look at the left and right side limits. So limit x approaches 1 from the left, and then also the limit as x approaches 1 from the right. So this is why I asked if the branches themselves were continuous functions, because now evaluating the limits, I can just do through direct substitution. So if I plug in 1 coming from the left, so numbers less than 1, we're going to be using that top function. It is continuous, so I can freely plug in the value. So that would give me an answer of 5. Coming from the right-hand side, numbers greater than 1, then that would give me an answer of 1. So we see here the left and the right hand limits not agree. Therefore, limit as x approaches 1 does not exist. So we did not meet the second condition. Therefore, is this function continuous at 1? The answer is no, not continuous at x equals 1. So even though, again, these were two continuous functions, they are not connecting together. And we would be able to clearly see that if we had made a graph to evaluate continuity, because then we would have had 2x plus 3, so it would have looked something like this. And then you had x squared picking up at 1. So let me actually read. So here's where you get that hole in the graph. And then here would be the rest. So there's my linear function. We get up to, this is at 1. We get to 1, going to make that jump down then to the parabola. Just going to pick up. So clearly, visually, if we could make a graph of this, we would have been able to make this conclusion a lot faster, because I would have just, okay, yeah, it's definitely not continuous. If we don't have access to the graphing calculator, or it's just too tedious to make the graph. So right now we're looking at just a 2-piece function here, but there might be 3 pieces or 4 pieces. So doing this analysis algebraically helps us to quickly determine, without having to go through the process of making a sketch of the graph, prove that this is in fact not continuous. Now, outside of this point, the function is continuous everywhere else, because we do know this part is continuous, this piece is continuous. So if I wanted to really describe the function f of x, I would say f of x is continuous for all values of x except at x equals 1. Because that's the part where the jump happens. Everywhere else, it's continuous. Because it's either I'm on the line, which I know is continuous, there's no holes or breaks in the graph there, or it's on the parabola, which I also know there's no holes or breaks in the graph either. So this is if I really wanted to describe the graph. Okay, we're good with moving forward and you know, describing it this way. All right, let's do one more. I'm going to move this right here, and I'm going to go ahead and pick another piecewise. Pick do one with big in it. So I've got tangent of pi over x, and have x. So I'm going to pick something that is not necessarily going to be nice. And then this is the one. Sorry, should be. This will be greater than or equal. Okay, so this is our function. Now our question is, I'm going to ask it. Is this continuous at x equals 1? Okay, so we know this part is continuous because it's a polynomial. But this part, we know we're going to start getting asymptotes depending on the x value because tangent does have asymptotes. Okay, so let's start off with the definition. So first condition, does f of 1 exist? So if we're at 1, we're going to be using this part of the function. So yeah, we can plug it in, and I do get f of 1 is 1. So yep, I met the first condition. F of 1 has an answer. Okay, second condition. Now, does the limit as x approaches 1 exist? So now we got to do the left and right side limits. So limit as 1 to the left, and then the limit x from the right. Okay, so if we're coming from the left, numbers less than 1, then that means we're going to be using the top function. Okay, so we know tangent. This is where your knowledge of functions will make things either go faster or go slower if you don't know. We know that tangent has asymptotes every what? Give you a moment here to kind of dig it out. It has asymptotes at every pi over 2. So there's asymptotes at pi over 2 and on and on. So when would this have be pi over 2? So because we don't have tangent of x, we have tangent of pi over 4 times x. So I just want to make sure that if we use 1, is it going to be on the asymptote if I use 1, or am I not on the asymptote, meaning it's okay for me to directly substitute? So this is why I want to just verify. So pi over 4x, if we were to plug in 1, that would give me tangent of pi over 4, which is an answer. It would give me the answer of 1. So we're good. This is not going to give me an asymptote. It's not going to yield that asymptote value because we're going to be looking is around 1. So we're good. I can directly substitute tangent of pi over 4 would be 1. When x is greater than 1, then we're using this bottom function. Okay, that I already know is continuous because it's a linear function. I can directly substitute. It's also going to give me 1. The values match. The left and right hand limits match. Therefore, yes. And I check off that second part. So now, do these two pieces match? That's my third condition. And the answer is yes, because they both are yielding 1. So f of x does in fact equal f of 1. So all three parts have been met. Therefore, f of x is continuous at x equals 1. So, without having to make a picture, without having to actually sit here and try to graph this thing to look at it, I was able to make a conclusion on the continuity of the graph at that particular point. So, if I were to draw it, I would be showing that at x equals 1, these two pieces of the graph, or however many pieces there might be, will connect, even though this would be really difficult actually to graph by hand because I'm having to deal with these conditions here. So absolute value of x is less than 1 actually translates to us doing this. And then this is translating to us doing like this. So this is a little bit more confusing to look at and then having to construct a graph. It's doable. I'm not saying it's impossible. It's doable, but you can see that would take a little bit more time to do than if I were to just kind of run through the definition. All right. So so in this video, we did a couple more examples of proving continuity of a graph, and again, using that definition of continuity. So you really want to make sure that you got that ingrained in your head of this definition of what it takes for us to know that a function is continuous.